everybody. Welcome back to Environmental Organic Chemistry with Dr. Lisa. So now we're going to do example problem 5-6 from the textbook. This is another problem about your buddy and mine, Freon 12. Yay, Freon 12, dichlorodifluoromethane. And so the purpose of this problem, kind of the gist of it, is that this is, first of all, getting you to think about the solubility of gases in water. And second of all, it's getting you to think about the Sessionow constant and the effect of salt on solubility. So we have some data here for the solubility of Freon 12 in fresh and seawater. So you're given this data in terms with the temperature in degrees Celsius and the solubility expressed in moles per liter here. And here I have taken the liberty of converting it to, 1 over T in Kelvin here, obviously by adding the 273.15 here, and taking just the natural log of the solubility. And notice that I put the seawater over here in a different column so that I could plot it all on one plot. So again, if we plot the natural log of the solubility versus 1 over temperature, we get a straight line. Notice that the slope here is positive. So remember, this is 1 over T, so to the left it's getting hot, and to the right it's getting cold. So over here where it's cold, these gases are more soluble in cold water than they are in hot water. Because they're gases, the way I think about this is that in hot water they're boiling out of the water. They're getting pushed out of the water because they're gases. If they were solids, I would say, oh, the water is warmer and therefore it has more energy to dissolve the solid, but because it's a gas, the gas is sort of being pushed out or boiled away. That's the way I think about it. I don't know if it helps you. Okay, notice also that this is the solubility of these chemicals given at 1 bar, which is basically the same thing as 1 atmosphere of pressure. That is how we typically define the solubility of a gas. Of course, in the real world, the partial pressure, the concentration of Freon 12 in the atmosphere is nothing like, 1 atmosphere. If it was, we would all suffocate. But I suppose this could be possible, inside a refrigerator, or in your air conditioning unit or something. But anyway, so here's the solubility in freshwater and seawater. And notice, okay, here's the freshwater in blue and the seawater is in pink. So the solubility in freshwater is a little bit higher than the solubility in seawater. Otherwise, these two lines are pretty much parallel, which basically means that the offset here in concentration and solubility is pretty much a constant factor at any given temperature. Okay, so that's important to know, to understand. So, I always like to make you plot in this version where it's the natural log of the equilibrium constant versus 1 over temperature. But then I also like to make you plot these things in terms of straight, in this case, solubility versus straight temperature, to notice that there is curvature here. And again, as I was explaining in the previous graph, at low temperature the solubility is high, and at high temperature the solubility is low. So solubility of a gas decreases as the temperature increases. It's a little counterintuitive, but it is nonetheless true. The solubility of a gas decreases as the temperature increases. And again, solubility in the fresh water in blue is higher than the solubility in the salt water in orange. Seawater, which has, 0.5 molar salinity. Okay, one of the things you're asked, so here's my slope and intercept on both of those curves. One of the things you're asked to do is to estimate the solubility of your compound, this Freon 12 in fresh and seawater at 5 and 25 degrees Celsius. So then you would just take your slope and intercept. Y equals mx plus b, and y is the solubility. So you just plug in the 1 over temperature here, and you calculate out, this is the log of the solubility here. And then here I've converted it from log into straight up solubility. And you notice again that there's a difference between the solubility in the freshwater and the seawater. The seawater should be a little bit lower than the freshwater, and the solubility at low temperature should be greater than the solubility at high temperature. Now notice that this compound is a gas throughout this entire range of temperatures. Remember, I don't know if you remember, maybe you remember, that back in the first lecture about vapor pressure, that whole module, we did an example problem with Freon 12, and we figured out that the boiling point of Freon 12 was minus 30 degrees Celsius. And since we're talking about aqueous solubility, we don't need to worry about the region where Freon 12 is a liquid, because at that point, water is no longer liquid itself. It is now a solid. It's ice. Okay, so that's how you would estimate the solubility in fresh and seawater at 5 and 25 degrees Celsius. One of the other questions you're asked to do is to derive the excess enthalpy of dissolution of your chemical. So that, to derive the excess enthalpy of dissolution, we know that is what we have been calling HE, HEW. And in this particular case, it's going to be equal to delta H of vaporization plus the delta H to get the chemical to move from water to air. Okay, and this is part of the reason why we chose Freon 12 for this problem, because we already figured out delta H of vaporization for Freon 12 in that previous example problem in the vapor pressure lecture. We figured out that the delta H of vaporization is about 20 kilojoules per mole from problem 4.2. Okay, so we already know this. If you want to know how to figure it out, you have to go watch that other video. And then we need to figure out this delta H for moving from water to air. Now, one of the things I want to point out here is that when you're talking about the solubility of a gas in water, you're getting perilously close to talking about Henry's law, right? I mean, it's basically the same thing, except that Henry's law is usually we're talking about liquids and solids. But there's Henry's law constants for gases too. So when you're talking about the aqueous solubility of a gas, you really are talking about Henry's law. So some of what I'm saying here is totally applicable to when we start talking about Henry's law in the next lecture. So where do we get this delta H water to air? Well, we get it from this plot right here. That's why we calculated the slope. And so from that slope, I'm calculating, taking the slope, multiplying by 8.314 joules per mole degree Kelvin, dividing by 1,000 to convert to kilojoules, and I get minus 28.8 kilojoules per mole in fresh water, and in seawater I get something slightly smaller, minus 27.9, so off by about a kilojoule per mole. And that's fine. That's allowed. It doesn't have to be the same thing. In fact, it shouldn't be the same thing, because if it was the same thing, then you would have the same solubility in fresh and seawater, and you don't. Okay, so now my question is, what is delta H excess, this HE excess term? What is this? And so this is where it's very easy to get confused about the signs. And so I have some text here, and I'll try to explain this in words. Do you add or subtract delta H of vaporization from this number? Well, again, the key is to think a little bit just in terms of absolute magnitudes, that these numbers are greater than this number in magnitude. Forget about the sign, just focus on the magnitude. It takes more energy to get this compound into the water from the gas phase than it does to get it from the gas phase into the condensed liquid phase, the pure liquid phase. So the plots above show you that the solubility increases as the temperature decreases, and that tells you right there that the delta H of this process is negative. And we know that energy is released when the gas dissolves in water, because delta H of vaporization is released, i.e. the gas is condensing. So that's a release of energy. If we were vaporizing, we'd be absorbing energy, but we're condensing. And we know that delta H of vaporization is always positive. So the gas to aqueous transition is more favorable. That's what these numbers are showing you, that this transition is more favorable than you would get just from the release of delta H of vaporization. So in other words, the slope is greater than the slope. The slope of this curve, these curves for water, are greater than the slope that you would get for delta H of vape. If we were plotting natural log of vapor pressure versus 1 over T, your slope would be not quite so steep. Okay? And so that's telling you that this HE excess term, this term, must be negative. So we subtract the 20.3 off from these two terms, and we get minus 8.5 or minus 7.6 kilojoules per mole. And as always, we ask ourselves, does this make any sense? And so we go over to our handy table over here. This is enthalpic and entropic contributions to the excess free energy of a series of organic compounds in saturated and dilute aqueous solution. And you notice one of the top ones here is trichloromethane, which is pretty similar to Freon 12. And the HE term is, depending on whether you're talking about saturated or dilute, it's -2 to +3. Now we are at saturated conditions, right? Because this is CSAT, this is solubility, saturated. So under saturated conditions, we do expect it to be slightly negative. And in fact, we are. And this is not, it's not outside the realm of possibility. There's some things here that do have a negative HE term. Now, most of them are hydrogen bonding, pentanone, tetrachloromethane. Well, tetrachloromethane is not hydrogen bonding, not particularly, not at all. So the fact that we get -4 here is a little bit, makes me feel good. Makes me feel good about these values of about -8 kilojoules per mole. Seem to make sense when compared to other compounds. So I feel good about that number. I'm happy. And then the last thing I'm asking you to do here is calculate the Sessionow constant. We know that the Sessionow constant equation is given here. It's saying that the activity coefficient of the compound in the presence of salt is equal to the activity coefficient when there's no salt, multiplied by this correction factor, which is 10 to the factor to the power of the Sessionow constant times the molar salt concentration. And we know that in seawater, molar salt concentration is 0.5 molar. So we can turn this equation around. It's a little bit funky the way it gets turned around, but this is your equation to calculate Ks. And here's your number. Let's make this a little bit bigger so you can see it a little bit better. There you go. So it's again, the ratio of these two concentrations divided by the molar salt concentration, which is 0.5 for seawater, 0.5 moles per liter. So we get a Sessionow constant of 0.35 at 5 degrees centigrade and 0.32 at 25 degrees centigrade. So pretty close. You notice one of the things you should notice too here is that our squareds are still pretty good, 0.99, 0.99, but there's a little bit of variability in the data points. And like here, you can see if we took the Sessionow constant here, we might get a slightly different value than we do like over here. But that's mostly just random variability. It's not really very meaningful. There's no discernible trend here. So this is just kind of natural variability. And then again, our big question is, does this make any sense? Does a Sessionow constant of 0.35 make sense for Freon 12? So again, we can go look at some other similar compounds. Here's some salting constants or Sessionow constants for a bunch of different organic chemicals. Here's trichloromethane, 0.2, trichlorofluoromethane, which is about as close as you're going to get to what we're looking at, 0.3. And so this value of 0.35 is not outside the realm of possibility. This is quite reasonable. So we get a reasonable Sessionow constant. So again, we're thinking now about the solubility of a gas. Solubility of the gas increases as the temperature decreases. Kind of counterintuitive, but that's the way it works. And the second thing we're thinking about here is how the solubility of anything, any organic chemical, can be suppressed by the salt in the water.